Under this water is a 50-kilometer railway link that changed Europe forever. This tunnel wasn't built against rock. It was built against the sea.
We're about to walk through how engineers drilled a railway under the English Channel and made it safe enough for high-speed trains.
This link is over 50 kilometres long and most of it runs under the seabed. It's basically a submarine mission for trains.
2 countries, 1 tunnel, and a stretch of seabed that engineers had to drill through without letting the ocean win.
The big enemy down there is water pressure. One mistake and the sea tries to move in.
Before a single metre was dug, the UK and France had to agree on law, safety, and who pays for what.
The whole route depends on one sweet spot underground, a chalk marl layer that's strong, predictable, and less leaky.
You can't just aim and hope. They built a survey spine so both sides meet under the water with almost no error.
It's not 1 tunnel, it's 3. 2 for trains and a service tunnel in the middle for access and emergency escape.
A tunnel is a factory line. You need power, concrete, rail carts, ventilation, and non-stop spoil removal.
First job, build the mouths of the tunnel and the underground access that lets TBMs even fit.
On the French side, they go down a big shaft at Sangatte to reach the right depth and launch machines toward England. This is the Star, a tunnel boring machine, basically a moving underground factory that eats rock and builds a tunnel behind it. Phase 1 is all about control. Nail the geology, build the portals, and launch the service tunnel to scout ahead.
They start with the smaller service tunnel first. It's the scout that tells you what's coming before you commit the big bores.
Every few meters, the machine installs a ring of concrete segments. That lining is what keeps the ground stable and water out. Behind the lining, they inject grout to fill voids. No gaps, no surprises, because the sea is always trying to find a path.
Everything the cutter eats has to leave. If spoil backs up, the whole tunnel factory stops.
You don't dig a tunnel, you move a mountain, one conveyor belt at a time.
They're constantly checking alignment. Drift too far and you hit worse ground, or miss the meetup entirely. Even in good rock, you get seepage. Pumps, drains, and inspection points keep the tunnel dry and predictable. Fresh air is life down here. Vent ducts push clean air forward and pull dust and fumes back.
This is high-risk work, so every shift starts with checks. Gas monitors, comms, lighting, and escape routes.
Some parts are bigger than a normal tunnel. They carve out caverns for crossovers and equipment rooms. To line 50 kilometers, you need thousands of identical segments. This is precision manufacturing, not guesswork.
Now the real race begins. Multiple TBMs from both countries, all aiming to meet under the channel with millimeter-level precision.
They don't dig 1 tunnel and call it a day. They dig 3 bores in a coordinated choreography.
On the French side, ground can be trickier, so they control the face pressure like a submarine bulkhead. In stable chalk marl, they can move faster. But fast only counts if your line and lining are perfect.
They recheck the tunnel's spine constantly. Under the sea, you don't get a second chance.
As they go, they plan cross passages. These will be the escape routes and maintenance access forever.
Trains act like plungers, pushing air. Relief ducts let pressure waves move safely so passengers don't feel a punch in the ears.
The service tunnel is the lifeline. It carries people, parts, and rescue access while the main bores keep advancing. These side rooms become the tunnel's organs: power distribution, communications, ventilation controls, and monitoring.
Waterproofing is mostly about details. Gaskets, bolts, and rings that stay perfectly round under pressure. When water shows up, crews treat it immediately. Small leaks are manageable, but only if you stay ahead.
This runs like a relay race. Hand off the machine, keep the line, keep the pace, no drama.
The service tunnel scouts the route. Now the two big rail tunnels follow, and everything gets louder, heavier, and faster. These bores are big enough for trains, cables, walkways, and airflow. That means bigger machines and heavier logistics.
Here, face pressure is the difference between stable ground and a messy collapse. Operators treat it like flying an aircraft. Some machines send muck out as slurry. Then surface plants separate solids, recycle water, and keep the TBM fed and stable.
Segment delivery is a heartbeat. Miss a beat, the whole operation stalls under the sea. Cross passages connect rail tunnels to the service tunnel at regular intervals, so there's always a way out.
They instrument the tunnel like a patient in ICU. Watch movement, pressure, and seepage so small issues never grow.
The scale is hard to grasp until you're inside it. Ring after ring, kilometer after kilometer.
At the face, it's controlled chaos. Cut, support, line, grout, repeat.
This is the TBM's breathing cycle. Install a ring, push forward, and lock the ground behind you.
As the two sides get close, every measurement becomes a headline. Miss by meters, and you've got a very expensive problem.
Right before breakthrough, they slow down and verify everything: line, grade, and ground behavior. This is the moment everyone waits for. Two tunnel crews, two countries, and one tiny point under the seabed where they finally meet. The service tunnel meets first. A small hole, a huge milestone, a continuous route under the sea. They don't just celebrate, they measure. The proof is alignment, not applause. Now the main rail tunnels follow. The opening is bigger, and the consequences of mistakes are even bigger. Hundreds of cross passages make the tunnel survivable. In an emergency, the service tunnel is the protected escape route.
Relief ducts connect the rail tunnels, so pressure waves can share space instead of slamming passengers.
These crossovers let trains switch tunnels for maintenance and operations. Think of them as underground interchanges.
Once the boring ends, the tunnel shifts from excavation to infrastructure. Surfaces get finished for cables, lighting, and walkways.
Rail doesn't forgive sloppy geometry. The base is built to tight tolerances, so trains run smooth at speed.
A tunnel isn't just for trains. It needs safe walkways and access for crews, inspections, and repairs.
Power, comms, sensors, lighting. Miles of cable turn a hole in the ground into a controlled railway.
They feed the tunnel from both countries. Redundancy is the theme. If one side trips, the other can keep essentials alive. Digging the tunnel is only half the job. Now we install the systems that make trains safe, fast, and controllable under the sea.
This is where it starts to feel like a real railway. Alignment, fastening, and smooth joints matter at speed. Power comes from overhead electrification in the tunnel. It's precise work because clearances are tight and reliability is everything.
Under the channel, trains rely on robust signaling and automatic protection. You don't want surprises at 200+ kilometers an hour.
Comms are non-negotiable. Operator radios, train-to-control links, and emergency channels all run through here.
Tens of thousands of lights make the tunnel workable and safe, even in power loss scenarios.
Ventilation isn't just comfort. It's how you control smoke, heat, and pressure if anything goes wrong.
Water always wins, unless you design for it. Drainage and pumping are constant, quiet heroes.
Fire protection is layered. Water supply points, compartment doors, and procedures that move people into the service tunnel.
These doors help isolate sections, control airflow, and guide evacuation. It's submarine thinking applied to rail.
Everything reports to control. Trains, airflow, power, alarms, and response teams. This is where decisions are made fast.
Now comes the nerve-wracking part. You don't test one system. You test everything as a single machine.
If you remember one thing, the service tunnel is the safety backbone. It's how you evacuate and how responders reach trouble.
In a problem, you don't run down the rail tunnel. You cross into the service tunnel, where responders can operate safely. Ventilation can be reconfigured to push smoke away from people and toward extraction routes.
Bolts is planned like aviation. Teams stage in the service tunnel and move to the nearest cross passage.
The cross passage network turns a 50-kilometer tunnel into manageable segments with multiple access points.
Redundancy is everywhere. If one feed drops, critical systems keep running so crews can respond.
When a train blasts through, air moves fast. That's why relief ducts and controlled ventilation matter.
Drills test the full chain. Control center, responders, ventilation changes,
and evacuation flow.
Before passengers ever ride, engineers walk it, touch it, and try to break it in their heads.
They time everything. In emergencies, minutes are the real currency.
When systems stop being construction and start being operations, the tunnel finally feels alive.
Now we test it like it'll be used. Real trains, real speed, real airflow, and zero tolerance for surprises.
First runs are slow. You listen for vibration, watch clearances, and confirm signals and comms are rock solid.
They load the system and watch for hotspots, contact issues, and power stability across long stretches.
Signals, speed supervision, and control room coordination get tested again and again, because this is where safety lives.
They hunt for dead spots. In a long tunnel, consistent radio coverage is part of emergency readiness.
At speed, airflow becomes a system test. Pressure relief, ventilation, and sealing all get proven in seconds.
They rehearse abnormal events, controlled stops, comms confirmations, ventilation adjustments, and access planning.
Even with a train stopped, the plan is the same. Guide people across, isolate airflow, and keep responders mobile. Commissioning all proves maintainability. If crews can't reach things fast, you redesign before opening.
Now it's endurance, run after run, measuring heat, vibration, pressure, and timing until it's boring in the best way.
You can feel the shift, from mud and concrete to clean operations. The tunnel is about to become routine.
The goal is simple. When the first passengers ride, nothing feels dramatic. It just works.
Once it opens, this stops being a mega project and becomes an everyday machine moving people and freight between countries.
Now it's real. Scheduled trains, strict timing, and a tunnel that has to be safe 24/7.
The tunnel isn't just passengers. Vehicle shuttles carry cars and trucks through like a rolling garage.
Freight is where the tunnel becomes an economic artery. Heavy loads, strict clearances, and non-stop scheduling.
Control balances passenger, freight, and shuttle traffic while keeping safe spacing and contingency plans ready.
In operations, the tunnel is continuously monitored. The boring part is the success. Maintenance happens when passengers sleep. Crews inspect rails, wiring, and systems before the next day's traffic. Overhead electrification gets inspected like aircraft hardware. Small wear today prevents big failures tomorrow. Even decades later, water management is a routine battle. You check drains, pumps, and sumps constantly. The tunnel gets scanned and monitored, because long-term stability is about catching tiny changes early.
Safety isn't a one-time design feature. It's a habit, practiced and updated.
When it works, it looks simple. That's the point. Massive engineering hidden behind everyday travel.
Build is a sprint. Maintenance is a marathon. This tunnel stays safe because crews treat it like a living system.
Patrol runs check systems and access points. It's like a daily health scan for the whole link.
Doors are simple, but they're mission critical. If they don't seal, airflow control and evacuation get harder. Technology changes faster than concrete. The tunnel's design makes upgrades possible without stopping everything.
Track gets measured constantly. Tiny shifts can become big wear at speed, so they correct early.
Overhead systems get retentioned and checked so contact stays stable and wear stays low. Ventilation is the tunnel's lungs. Keeping fans and dampers healthy is non-negotiable.
Control systems get tested and maintained too. Reliability comes from boring, repeated checks.
All that work turns into something simple. You leave one country and arrive in another with the sea above your head.
The most mind-blowing part is the undersea section. It's long, deep, and built to stay stable for generations.
2 portals, 1 link. The tunnel is invisible from above, but it rewired travel beneath the water.
The real achievement is how normal it feels. That normal took geology, math, machines, and decades of learning.
So what's the real legacy? Not just a tunnel, but a reliable corridor that has to work every single day.
This link moves people, goods, and time. It turns borders into schedules instead of barriers.
For passengers, it's just a comfortable ride. The engineering disappears, which is exactly the point.
Survey, geology, 3 tunnels, TBMs, lining rings, cross passages, pressure relief, then rail systems, and non-stop monitoring.
That's the payoff. A train running under the sea safely again and again, like it's the most normal thing in the world.
And behind every train run, this quiet service tunnel keeps the whole system maintainable and safe.
All right, that's the Chunnel Tunnel. Built like a submarine, run like a railway, and still one of the wildest engineering links on Earth.